Good morning, students. Today we are going to discuss about the operational amplifier. It is an important topic regarding in this unit. Operational amplifier is basically an analog device which helps to do all the mathematical formulation. For example, addition, subtraction, integration, differentiation, all the things we can able to do with the help of this operational amplifier. It is simply referred as a OP-amp, OP-AMP, operational amplifier. And it also helps to do rectifier, oscillators, many applications we can able to incorporate with the help of this operational amplifier. So what's the internal content of the operational amplifier is, it consists of many resistors, capacitors and also the transistors which are being interconnected in a proper manner. It is also referred as a in the form of integrated circuit. It is referred as a IC, integrated circuit. What is ideal amplifier? It is a symbolic representation of the ideal amplifier. Here we have two inputs. One is a negative input and another is a positive input. Negative input is always referred as a inverting input and the positive input is referred as a non-inverting input. You have to keep it in mind. The minus is referred as a inverting input, positive is nothing but a non-inverting input. What happens when you are giving input in the inverting terminal? The output will getting a negative value. That means 180 degree out of phase. In case of non-inverting, if we give a input in a plus, output will be in a positive. This is the only difference we have to understand that. The plus 5 and minus 5 is for giving a proper biasing of an operational amplifier output terminal. What's the internal content? So V1 and V2 are the two inputs. As usual, V1 is referred as a inverting and V2 is referred as a non-inverting. Rin is referred as a internal resistance of the amplifier, and R0 is the output resistance, V0 is the output voltage, A is the amplification gain, where Vd is nothing but difference in voltage, that means V2 minus V1. This is a representation here. And also we have to understand that the characteristics of the ideal amplifier. It is they will ask in 2 marks. What are the main ideal characteristics of a op-amp? It is having a very high input resistance impedance, that means in case of around infinity, and having a low output resistance, that means nearly equal to 0. You have to understand that in case of a bipolar junction transistor, the input resistance is low, the output resistance is high. So here it is having a reverse. It is also having a very high open loop gain. It is referred as A is equal to infinity. Input bias current is referred as 0. When the two inputs V1 is equal to U2, the output will be a 0, infinite band gap, and it is also having a common mode rejection ratio CMMR. We will discuss later. It is having infinite slew rate, unity gain frequency. So these are the few characteristics of an ideal amplifier. So here we are going to discuss about the inverting amplifier and non-inverting amplifier one by one. It is simple. We are going to apply the simple logic of Kirchhoff's voltage law. Then potential divider, we have discussed it in very first unit itself. We have discussed the potential divider rule. We just to recollect these things. So inverting amplifier is one of the application of the op-amp. So we have started to discuss about the application of amplifier op-amp. So what I am telling, inverting amplifier would give the input in the negative terminal, that means V1 through R1. FB is nothing but a feedback resistance. The output is V0 is fed back to the input terminal. V2 is grounded. So when the V2 is grounded means the junction of R1 and RF is also having the same potential of V2 is equal to 0. It is very important thing you have to understand. I am repeating, V2 is grounded, that means the potential at R1 and RF joining point node is also a 0 potential. Then I would like to calculate the current which is flowing through the R1 resistance. So potential difference between the two ends of the resistance divided by the resistance value give the I1. That means V1 minus V2 divided by R1 is equal to I1. This is expression. V1 minus V2 divided by R1 is our expression. And you have to understand that V2 make a 0. That means V2 is ground potential. So I1 is nothing but input voltage divided by the R1 resistance. Then come to the output voltage. V0 is nothing but minus I1 into RFB, that means feedback resistance. Substitute I1 form here V1 by R1. So rearrange the expression, the V0 is equal to V1 by R1 into RFB, that means feedback resistance. Then for inverting amplifier we can able to calculate the gain, voltage gain is equal to AC V0 by Vn, that means output voltage divided by input voltage. Output, substitute the output voltage minus V1 divided by R1 RFB, V1 is going to get cancelled. The gain is nothing but minus of RF by R1. So by keep on adjusting the value of these two resistance, the gain of amplifier is adjusted. Okay. You can notice that the output is negative, that means it is an inverting amplifier. The non-inverting amplifier, the another application is also a non-inverting amplifier. So here definitely what will be the output of the V0 is a positive. Okay, let us see that. The input may be a AC or DC. We can able to provide inverting and non-inverting amplifiers. These arrangements we have. Here instead of V1 it is grounded. Vn is given here. Okay. So here we can the junction point of R1 and RF is for A. In earlier itself I am telling that this point A is also a V1 right now. Okay. By simply applying the potential divider rule at this point, we can able to write Vin divided by R1, which is equal to V0 divided by R1 plus RFB. You please say that V1 divided by V1 is applied here, it is ground. So V1 is divided by R1, which is equal to V0 by this is a potential divider R1 plus RFB. So rearrange the equation, V0 by Vn is equal to R1 plus RFB divided by R1. So by simplifying we had a gain V0 by Vn is equal to 1 plus Rf by R1. So here we can notice that whatever may be the value of the resistance R1 and RFB, the gain of the amplifier is always greater than 1 and output is also a positive. And another applications of FM with respect to the mathematical relevancy. Summer amplifier, both if you are giving input in a inverting, it is referred as a inverting summer amplifier. If you are giving input in the positive, that means non-inverting, it is referred as a non-inverting summer amplifier. Simple knowing of KCL, we can able to do this formulation. The summer amplifier is a one which produces the summation of different input analog signals applied at the input terminals. Here you assume that the VA, VB, VC are the different input analog voltages. In the case of output, we can able to get it. But I am giving the input in the inverting amplifier. So what would be the output V0? It is in terms of negative. Okay. So with respect to selection of RA, RB, RC and RFB, we can able to make V0 is equal to minus of VA plus VB plus VC. Otherwise, V0 is equal to 1 by 3 of VA plus VB plus VC. That depends upon our selection of the resistance. That depends upon our design also. You notice that RA, RB, RC are the voltage resistance associated with the VA, VB, VC terminal, and the feedback resistance is RFB, and the non-inverting terminal is connected to the ground. So what is the purpose of compensation, which is we can also able to calculate. So apply the KCL at this node, at this point, VA minus VN divided by RA plus VB minus VN divided by RB plus VC minus VN divided by RC. So these are the incoming current. Then outgoing current is nothing but V0 by RFB. So these are things I have written. The Vn is already connected with the ground potential, so Vn is also 0. In earlier we have discussed here, I will refer it. So here V1 minus V2 divided by R1, V2 is ground potential, so we are making a V2 as 0. So here also we are doing the same. VA minus Vn, VB minus Vn, VC minus Vn. So Vn is making a ground potential. And V0 is equal to, rearrange the equation, we have minus of feedback resistance by RA, VA, etc. So the negative sign which indicates the inverted output. We are already knowing that when you are giving the input in the inverting mode, the output will be in a 180 degree or a negative value. The proper selection of resistance we get. If we make all the resistance including feedback as same, then we cancel each other, then the output voltage is equal to summation of all the three inputs. N number of inputs can be given. In case of RA, RB, RC which is equal to 3 times of the feedback resistance, means we can able to get the output voltage as a average value. Okay. And R compensation, by making all the three input voltages are equal to 0, VA, VB, VC is equal to 0, substitute here, it will be equal to R compensation is R input is parallel to R feedback. So what is R input? What is our R input? These three are connected in parallel. So RA parallel, RB parallel, RC parallel with RFB parallel. So this value which decide the R compensation. This is related to the inverting amplifier. Then come to the non-inverting summer amplifier. The same input VA, VB, VC is given to the non-inverting terminal, and as usual we are keeping the inverting terminal as a ground. Okay. So here also we are going to apply the KCL here. VA minus VN divided by RA, VB minus VN divided by RB plus VC minus VN divided by RB, which is equal to 0. In case of inverting amplifier, we are considering incoming current is equal to outgoing current. The incoming currents are VA minus VN divided by RA, VB minus VN divided by RB, VC minus VN divided by RA, and outgoing current is V0 by RF. So here we have only these points. So incoming current only. Okay. So rearrange the equation. Vn is equal to VA, VB, VC divided by this value. What is the output expression for the case of non-inverting amplifier? We have already derived. Can you recollect this expression? In case of input is given in the non-inverting amplifier, the output voltage is 1 plus R feedback plus R into Vn. I can show it again. In case of, yes, here, this is the expression. V0 is by Vn is equal to 1 plus RFB by Rn. This is for non-inverting amplifier. The same is implemented with more than one source. That's all. Nothing is a difference. So Rf by Rn is equal to Vn. Substitute Vn here. So here also we can able to select with the selection of RA, RB, RC is equal to feedback divided by 2. The value will be equal to summation of plus VA plus VB plus VC. Here the output is given, the input is given in a non-inverting, so output will be a positive. Okay. Then another, these two are referred as a summation of inputs when you are giving to the inverting mode and non-inverting mode. Then come to the difference amplifier. Difference is nothing but subtraction. Okay. So here the VA and VB are given to the inverting and non-inverting amplifier respectively. RA and RB are the input, and RFB is also a feedback resistance. What is the value expected output in a V0 in case of difference amplifier is VB minus VA. Okay. And all the resistance are made as a equal to same value. We are going to discuss the superposition principle. What is superposition principle? In the first unit itself we have studied. When the system having a two input, the circuit can be analyzed by keeping one source alone and making another one is 0. Then the same analysis has to be repeated for the second source. Consider the second source and they make the first one as a 0. So in this way we are going to discuss the one by one. But the thing is, we are going to apply the inverting mode voltage expression and non-inverting mode expression. You think that the output voltage VB1 due to the VB, when the VB is considered, it is referred as the output voltage is VB1, and we make V is equal to 0. And we know that what is the expression for non-inverting? Output voltage VB1 is equal to input voltage into 1 plus, here RF is also considered here RA, or otherwise we can able to have a expression of RF. Okay, we can able to do anything. But as per formula, the feedback resistance divided by RA. So here they have put both RA and RA. You just change it. Feedback resistance divided by RA, which is equal to VB. Why I have put Vn is equal to Vb by 2. Here the Vb is applied across the two resistance. It is getting potentially divided. These two are same wire resistance, so the applied voltage Vb is divided by 2. Vb2 here, Vb2 here. Together Vb by 2 plus Vb by 2, which give the Vb. So the input is here is Vb by 2. This is the one we have to understand. Okay. Similarly, Va alone consider, make a Vb as a 0. Then what happened? We have a well-known expression that the output voltage A1 is equal to minus of feedback resistance RFB divided by RA into input voltage VA. So this RFA, RA all values are same, so it can cancel each other. So input voltage VA1 is equal to minus of VA. So combine the effect of these two expression. When the VB is alone, VA is alone, we have an expression. So VA is equal to VA1 plus VB2. VA1 is expressed as minus VA, VB2 is expressed as VB. So output voltage V0 is equal to VB minus VA. This is the difference of amplifier. So the output is getting difference of V1 and V2. As usual, the value of VA and VB is given with respect to our own design. RA, RB value can also be, we can design accordingly. And another important application is a integrator. Followed by the integrator, we are going to discover the differentiator. These two circuits are same. The only thing is the resistance and the capacitance are interchanged. When you are discussing about the integrator, the input V1 is applied to the resistance, the feedback is a capacitance. But in case of differentiator, the input is given through the capacitance and the feedback is through the resistance. This is very important. And we are going to apply the simple KCL. All the op-amp circuits we are simply using the Kirchhoff's current law. The incoming current is equal to outgoing current, or the sum of current at the junction is made 0. Algebraic sum of current at a point is 0. In both cases, integrator differentiator, we are giving input to the only inverting mode alone. Okay. In case of here also we are giving input mode in a inverting mode. Here also we are giving input in the inverting mode. It is one of the application of linear op-amp which performs the mathematical operation of the integrator. So what will happen when the input, here also it is grounded, so Vn is also 0 potential. Apply the KCL here. Incoming current is equal to outgoing current. Here is feedback current. Incoming current is equal to V1 minus Vn divided by RA. Vn is made 0 because of this non-inverting potential is 0. So V1 by RA comes plus feedback current through the capacitance. The current flowing through the capacitance expression is C into dV by dt. It is very basic basic formula, unknown formula. Capacitance into dV0 by dVt, because the V0 is a one output which is fed back to the input through the capacitance. So C if the feedback resistance into dV0 by dt is equal to dt. We are interested in taking the integration. Take the derivative part from left side and rearrange the equation. We have a right side in this equation. Integrating on both sides, the limit will be 0 to t. So by taking the derivative of dV0, we have a V0 of t. Substitute upper and lower limit, we have V0 of t is minus, lower limit V0 of naught. So this V0 of naught is bring to the right hand side as a positive, and I keep this expression as it is. So with respect to R value, with respect to C value, and input signal will be integrated. When you give the AC sine wave, it will be integrated in an output. So what's the integration of sine wave? Is a cos theta. Means a cos theta. So V0 is equal to minus this minus, which indicates the we are giving input in the inverting mode. And another important thing is the integrator and the differentiator, we have a time constant T. This is nothing but R into C, RA into feedback resistance is referred as a integrated time constant. You come here the differentiator. Here the same circuit as integrated. The only thing is I already told that the capacitance as in input, feedback resistance is output. Here also we are giving input in the integrating mode. So find the voltage at integrator. and ground potential is Vn is equal to 0. The current flowing through the capacitance Ia is equal. Here also I am going to apply the both incoming current and outgoing current separately, and I am going to add it. Incoming current can be calculated by current flowing through the capacitance is equal to C into dV by dt. Voltage is V1 minus Vn, and Vn is 0 because of the non-inverting mode is connected to the ground potential. So we have a C into dV1 by dt, and current through the feedback resistance is equal to V0 by Rf. So by applying the KCL at this node, you can add these two things, C into dV by dt plus V0 by Rf is equal to 0. We are interested in taking the output voltage V0, so rearrange the formula. R into C is also here is a time constant dV1 by dV2. That means the input voltage is taking derivative. Here the input voltage V1 is taking integrated. So this is an integrated circuit, this is a differentiator circuit. The gain is always known as, before that, here we can able to take the representation of phasor representation. So V0 of S equal to R into C for constant. Derivative term is referred to as S into V1 of S. That you have studied in the max. Derivative of V1 by dt is nothing but S into V1 of S. And in case of S, we can able to substitute the j omega. So gain is in terms of omega, we can represent the V1 even get cancelled. S can be referred as a omega. The magnitude is considered, while we are considering the magnitude, j can be omitted. So omega R into C is nothing but a gain. Also we can able to refer the Fa is equal to 1 by 2 pi R into Sc. So this is a important application of AFM with respect to the mathematical formation, inverting summation, non-inverting summation, then inverting amplifier, non-inverting amplifier, difference in amplifier, integrator, differentiator we have discussed. The next part we are going to discuss about the other applications, rectifier and oscillators. We will discuss next session.